Hello. Today we'll be learning about UVM, otherwise known as Universal Verification Methodology. Let's start with what UVM is. UVM is a standard practice to enable faster development and the reuse of verification IP throughout the industry. So IP, otherwise known as our design, we are able to verify it through the use of UVM. So UVM works as a test bench that is very modifiable so that we can run any number of tests through it with any type of stimulus. Now, let's look at the advantages between UVM and our typical test bench setup like we did in digital design using VHDL. Now, UVM is a system Verilog library specifically designed for testing system Verilog designs. So the advantages between UVM is that UVM ensures test bench uniformity and creates set guidelines to be followed by the verification test benches. This means that any cause for error won't be on the UVM side, and it's very easy to set up simulations and tests through UVM. And it creates guidelines and uniformity. So uniformity means that the test bench will be able to be run by anyone, as well as that the test bench has certain set classes that we can set apart and are very configurable. Now, this allows tests to create randomized stimulus and verify functional correctness amongst other features. So the tests within UVM we can create ourselves, and it says we can randomize stimulus. Well, what does that mean? Well, if we had an adder design as our IP and we wanted to verify that our adder was functionally correct, we could create a test to input into our inputs on the adder, let's say in1 and in2 on our adder, and we can randomize within the UVM test any number of stimulus to be inputted into the adder. And then on the other side, we could also receive back the output of the adder and then confirm that it is functionally correct. So UVM also works with a C type, C++ type programming language. And so we can use if statements and such to essentially test that our design is correct. So if we input this stimulus randomized, we can then grab that data, both the input, the output, and what we inputted into our design from our test, and we can use if statements and such to check that it is functionally correct by simply creating a statement to say if the input of in1, if the product of in1 and in2 is not equal to the output that we received on our adder design, then the design is flawed and we can print out an error using UVM. So those are the advantages between your typical VHDL test bench, is that we can configure it and it allows us to do any number of things and debug easier, run any design that we would like through it, and test for protocols and such. So here is our figure. So we have our sequencer. So you can see the data will go from the sequencer to our driver. So within UVM, we have base classes and different types of objects. And so these are the different types of objects and classes. So our sequencer will house our data that we are testing. So our sequencer includes our sequence, which is our test, and our input data. So then that goes to our driver, which instantiates our design inputs and will then convert the data from the sequencer to the driver. And then the driver talks to our interface, and the interface communicates specifically between our DUT, and our DUT is our design. So it talks from our design through the interface to the driver. So specifically, the driver functions only with our inputs into the design, and then our interface in the monitor side allows us to grab the outputs from our design. And both the driver and the monitor talk directly to the scoreboard. So the scoreboard allows us then is where we would have our verification logic. So this is where our if statements would be in the case of the adder example. We would know the input data from the driver, the input variables from the driver, and then we would have the output data from our monitor. And inside of our scoreboard, we can then verify that our design is either correct or not correct. And here we can see that in action. So our data goes from the sequencer to the driver, then to the interface to our design. Our data is already in our scoreboard from the input, and then the output from the monitor goes into our scoreboard. And then we are able to test if the design passed or failed. Same thing, if we have a sequencer, it goes to our driver, interface, back and forth, and then to our monitor, and then to the scoreboard. So the interface can both deal with input and output, and then we can determine if our test failed or passed inside of our scoreboard. And so UVM allows us to very well structure our test bench designs by creating everything separately so that our design can be changed in any way we would like with very little effort. So here we have our classes. So as you can see in the figure below, we have our test and then our environment. So our test is going to be our main program. The environment is what is going to house our classes and our object types. So one of those object types is agent. And so the agent will hold the generator, driver, and monitor. The generator will generate our stimulus and then talk to the driver. The driver will then, as we looked at previously, interface, and then to our design will go the input signals, and then output from the design will go into our interface again, talk to the monitor, and then the monitor sends it back up to our scoreboard. And so our scoreboard and our agent is all housed inside our environment. So UVM provides a set of base classes from which more complex classes can be built by inheritance and adding onto it certain functions required for verification environment. So before, previously in our VHDL test benches, we would have to change the entire test bench to modify a specific test that we wanted to run. If we wanted to run random stimulus, it would be extremely difficult on VHDL. But with System Verilog and UVM, it is very easy, and that is why it is the industry standard. So now let's dive into UVM objects. So the idea behind UVM is to enhance flexibility and reuse of code so that the same test bench can be configured in different ways to build different components and provide different stimulus. These new user-defined configuration classes are recommended to be derived from UVM object. So UVM objects can consist of our monitor, scoreboard, interface, and such, and we can configure those in any way from a configuration class object. So example, a configuration class object can be built to have certain settings that define how the test bench environment is built. An example of this, specifically for UVM, would be that UVM allows us to print different levels of severity of errors in our code. And we can print different types, and it allows us to print that to our console or to the output of UVM. And this allows us to debug our code much better. UVM has these specific print statements already in its library, and they make it very easy. But a setting inside of our configuration class is one of the settings could be to print a specific type of severity. So we have the ability to configure our settings so that a certain type of severity is only printed or a certain type of severity is left out. So this means that you could set it so that your lower severity errors are set aside and you more focus on your higher severity errors. Because once we use things like UVM with our System Verilog design, you will see thousands of lines of errors. So it is much easier to go through the higher severity levels of errors and to focus out all of the lower severity errors. Now let's go into our UVM sequence. Now, the sequence is a container for the stimulus to the design. So the sequence houses our stimulus that we created inside of our test. So the sequence could be the randomized stimulus. So in our research, we are testing protocols specifically, and it is very good to use randomized stimulus to test protocols so you don't have to test every single edge case. As well, if you are testing a memory component, it is better to test the randomize the addresses of your memory component so that you don't have to test every single memory address, which would make it very difficult since when you're working with memory, it is oftentimes a very large memory space that you would need to test. But using UVM, we can test edge cases as well as use random stimulus to verify our design to the fullest ability. And then sequences can be used inside other sequences to create different types of scenarios. So let's say we had, back to our adder example, let's say we had a sequence that would allow us to randomize our input into the adder. We can create another sequence that will allow us to switch our inputs, switch our stimulus into the inputs. So we could set our in1 to be in2 and in2 to be in1 for stimulus to make sure that our design works completely. And then we can use that sequence inside of our randomized sequence to then randomize and then switch the inputs so that we can input our stimulus into in1 and in2 the same way that we can do in2 and in1. And another example of this would be a read and write to a memory entity where the address is random. So that is a more industry standard use for UVM randomizing through sequences. Now let's talk about UVM sequence items. Specifically, sequence items are the data signals that are input into the DUT or the design and are called through the sequence items class. So sequence items can be defined as your, let's say in an example, your read address, write address, clock, enable, etc. So all of your input designs, input signals into your design are referred to as sequence items and need to be instantiated inside of sequence items. And then your output goes back through your monitor, like we talked about, through the interface. So all of this comes together inside of UVM. Now talking about the UVM transaction class. So the field required to generate stimulus are declared in the transaction class. So as you can see on the right side, we have class transaction, and then we are declaring the transaction items. So these are our items inside our design. So our data signals inside our design, we can instantiate outside of that inside of our class transaction, as long as we give specific bits and such. And then we can use that and input those into our design through the interface. So the transaction class can also be used as a placeholder for the activity monitored by the monitor signals of the DUT signals. So this allows us to receive our data coming out of the design and monitor that through the transaction class. So not only input signals go into our class transaction, but also input and output signals. And then our generator sends transactions to be interpreted by the driver to provide stimulus to the design through the interface. The generator generates our stimulus, sends that stimulus through the transaction then sends it through the interface, and then the interface then sends it through the design, as we saw previously in our video example. The monitor then interprets the outputs of the design into transactions. So like we said, the transaction can take both input and output. So the monitor will send that back to the transaction class. And then the transaction class can be called upon from the scoreboard. And then the scoreboard is what allows us to verify our design. By having both the input and the output data, we can then write functions to verify our design in any way that we deem is correct for functionability. So here are our major UVM components. They include the UVM Driver, which we saw earlier, drives the signals to the design. We have our UVM Monitor that monitors the signals at the design output port. So those are your output data signals. We have UVM Sequencer, which creates different test patterns. So our UVM sequence, like we talked before, was our sequence that is our test. So we can randomize stimulus through that as well as any tests that we want to create custom. And then we have our UVM agent. This contains the sequencer, driver, and monitor. And then our UVM environment contains all other verification components, such as our scoreboard and any other components within the UVM verification. So print statements and such will go inside of our UVM environment. Then we have our UVM scoreboard, which houses as well the checker that determines if our test failed or passed. So this is where our logic comes into play, and our print statements can be also found here that we can print out of our UVM to the UVM logs. So this allows us to then check if our design is functionally correct. Here we have our UVM interface. So the interface is a type of object. And then the system Verilog construct. This is the system Verilog construct to encapsulate communication between modules. So our interface we looked at before allows us to talk to our design essentially. So it will convert the variables and such into data signals that can then be output or input into our design. This can also, the interface can also contain mod ports, which provides direction information for module interface ports and controls the use of tasks and functions within certain modules. So as seen at the bottom on lines 32 and 35, we have a mod port for our driver and our monitor. So the driver, as we talked before, will have our input signals. So this includes clocking signals, this includes reset, our input, any kind of stimulus that needs to be input. And then our monitor contains the output data signals that come from our design. And so the interface is also shared by multiple entities. As you can see, the driver, the monitor, and etc. are shared by the interface. And we'll see that later on, that they refer to the interface because the interface deals with both the input and output data and is needed in almost everything inside of UVM. Here we have our UVM driver. So the driver will talk through the sequence, and then the driver talks to the interface to talk to our design. So this is where the sequence or our test is converted into our signals that can be inputted then through the interface. So the driver class receives the stimulus from a generator in the form of a transaction shared through a mailbox. And then our driver converts transaction level data to signal level activity. Like we said previously, the driver will take the data from our stimulus and then convert that to signal data that can then be used inside of our design. So as you can see here on line 37, we have a write enable and a read enable that we are setting to 0. And not only that, we are setting also clock signals within our driver class. And then this allows us to set any signals that we would like, as well as drive interfaces. As you can see on lines 44 and 45, we have our driver interface, which is our write enable and write data. And then they talk as well through the transaction class, which houses, as we remember, our input and our output data signals. Moving on, we have our UVM monitor. So the UVM monitor samples the interface signals and converts signal level activity to transaction level. This allows us to send, so the UVM monitor sends transactions to Scoreboard via the mailbox. So this allows us to get our output data, like we said before, and then output that to our Scoreboard so that we can then verify the design. So as you can see here on line 9, the transaction class, talks to the address signals write enable and write data through our monitor. So the monitor then is our output data from our design, and it is then set to our transaction class, and then our transaction class is then picked up by the scoreboard. Now, after talking about our transaction class and our monitor, we move on to the scoreboard. So this is where our input and output signals are then grabbed from the transaction class to then be used in actual verification logic. So the scoreboard receives the sampled transaction from the monitor, and then it is used to perform the actual verification. Otherwise, is the output correct? Does my design pass or fail the test that I created for it? So in this case, we can see that the design is testing address verification. So that means that we can create random address data and use random addresses, and then input our data into an address. And if it works, we should be able to read from that same address and receive the same data that we wrote to that specific address. So within VHDL, this would be more difficult. Inside of UVM System Verilog, this becomes very easy, and we can randomize our data as well as provide arrays for our data to then be used in. Here we have our UVM generator. So this generates transactions that will be translated into stimulus for the design. So going back to the beginning, our generator deals with our sequences. So our sequences are our tests. So then the tests go through our generator, then translated into stimulus for our design through the interface and the driver. This also sends generated transactions to driver over mailbox. So we can see that if transaction randomize fails, then the transaction randomization failed, and we have a little print message. Now this print message is not custom to UVM. This is a system Verilog print message, and we will go into custom UVM print statements in our example later. Here we have our transaction. Do copy and then put. These are all functions within UVM, as well as randomize is a function within UVM, so you do not have to create a randomize function yourself. This is all contained within the UVM library to use. And this will then randomize our transaction and then drive it to our design. So all this becomes very neat and tidy within our UVM environment. So our UVM environment will declare generator, driver, monitor, scoreboard, as you can see, as well as events and virtual interfaces. So the virtual interface functions as our interface between our driver design and monitor. So our UVM environment contains instances of these and then provides an instance of the interface to all the classes that require it. So our class environment is what houses pretty much everything that talks to our design and is generated within UVM. And then the main task runs the main test. So this is where we can change where the which specific test is tested as well inside of our class environment. So this means that we can run multiple different types of tests inside of our same environment without even having to change our code. Here we have our UVM Testbench and Test. So the testbench top is our top level file, and then our test is our test that we want to perform on our design. So here we can see that the test bench is the top level entity in a module, and it instantiates the design, interface, and the test. As we can see on line 18, if this memory module DUT, or design, is then instantiated with the clock, reset, address, and other data signals. And then we instantiate that using our interface signals to connect them to our design ports. Now, the test is a module that instantiates the environment and calls its run procedure. So the test instantiates the environment and then calls the run procedure. So the run is the generator and driver main tasks. So this is where our main program will start from. This is also where we can set any environment variables that we would like, as well as any general variables that we can use throughout our design. So in this case, on line 12, we can see that it is setting the repeat count of generator as 4, mean to generate 4 packets. This means that it will run the test 4 times. And on line 9, we are instantiating the environment, as well as the interface through it as well. Here we can see this in a little bit more of a figure. So our test bench top is our top level. This is housed with, our test is housed within our test bench top, and then the environment is housed within our test. The environment contains the generator, which we remember is the data from our test that is then converted to our data signals that the design can understand inside of our driver, and then our interface interfaces with those signals through our design. And then once we receive an output from the design, it goes back into the interface. The interface stores it back in the monitor, which we remember that the monitor stores it in our transaction class, as well as the inputs are stored in our transaction class. That's why you can see that little box in the middle. And then from the transaction class, our scoreboard reads the transaction class, which contains both our input and our output data, and then verifies the design through there. Terms to remember: UVM is universal verification methodology, and DUT is device under test. So like we said, DUT is our device.